In this unit, we're going to have a look at a method for combining two vectors. This method is called the scalar product, and it's called the scalar product because when we calculate it, the result that we get, or the answer, is a scalar as opposed to a vector. So let's look at two vectors. Here's the first vector. Let's call that vector A. And here's a second vector. Let's call this vector B. And you'll notice that I've drawn these two vectors so that the tails of the two vectors coincide. Now that they coincide, we can measure this angle between the two vectors, and I'm going to label the angle theta. So there are our two vectors. Now when we calculate the scalar product, we do it like this. We find the length, or the magnitude, or the modulus of the first vector, which is the modulus of A. We multiply it by the length of the second vector, which is the modulus of B, and we multiply it by the cosine of this angle between the two vectors. We multiply it by the cosine of theta. And that's how we calculate the scalar product. The length of the first vector times the length of the second vector multiplied by the cosine of the angle in between the two vectors. And we have a notation for the scalar product, and we write it like this: vector A dot vector B. And this is the definition. Sometimes this scalar product is also referred to as a dot product because of that dot in there. So sometimes you'll hear it referred to as a dot product. Okay, so let's have an example and see if we can calculate the dot product of two vectors. Let's suppose our vector A here has got length 4 units. And let's suppose we have a vector B up here. And let's suppose vector B has length 5 units. And let's suppose that the angle, for the sake of argument, between the two vectors is 60 degrees. And let's use this formula to calculate the scalar product A dot B. That's a vector there. A dot B will be, well, it's the modulus, or the length of the first vector, which is 4, multiplied by the modulus, or the length of the second vector, and the length of the second vector is 5, multiplied by the cosine of the angle between the two. And so we want the cosine of 60 degrees. Now, the cosine of 60 degrees, if you don't know, you can work it out on your calculator, but it's a common angle, and the cosine of 60 degrees is a half. So we've got 4 multiplied by 5 multiplied by a half. So if we work all that out, we get 4 5s are 20, and a half of 20 is 10. So that's our first example of calculating a scalar product. And let me remind you of something that I said very early on, that when we calculate the scalar product, the answer is a scalar, and you'll see the answer here, 10, is just a single number. Whilst we started with two vectors, A and B, we finish up with just a single number, a scalar, and that's the scalar product. Let me illustrate some other features of this scalar product by doing the calculation the opposite way round. Supposing I'd try to calculate B dotted with A instead. Let's work that through and see what happens. So I've done the operation in a different order. Instead of A dot B, I've now got B dot A. Well, again, using the definition, we want to say that the dot product of B and A is the modulus or length of the first vector, which is the modulus or the length of B this time, and the modulus of B is 5, multiplied by the modulus or the length of the second vector, which is now 4, multiplied by the cosine of the angle between the two, and the angle is still 60 degrees. And the cosine of 60 degrees is a half. So if we work this out this time, we'll get 5 fours are 20, and a half of 20 is 10. So you'll see that whichever way we did the calculation, whether we worked out A dot B or whether we worked out B dotted with A, we get the same answer, 10. And that's true in general for any two vectors that we choose. If we work out A dot B, that will be the same as working out B dot A. And that's another important property of the scalar product, and we call this property commutativity. We say that the dot product or the scalar product is commutative. Now, as well as the commutativity property, I want to tell you about another property which is known as distributivity. Suppose we have A dotted with the sum of two vectors, B plus C. The distributivity property tells us to expand these brackets in the normal sort of algebraic way that you would expect. We work this out by saying it's A dotted with B added to A dotted with C. This also works the other way round. So suppose we have B plus C and we want to dot it with the vector A. As you might predict, the result that we'll get is B dotted with A added to C dotted with A. And these properties are said to be the distributivity rules. And we'll need those rules along with the commutativity rules later on in this unit. Now, there's another property, a very important property of the scalar product that I'd like to tell you about as well. And it's the scalar product of two perpendicular vectors. Let's see what happens when the two vectors that we're dealing with, A and B, are perpendicular. That means they're at right angles. So we have a situation like this. There's vector B, there's vector A, and they're separated by an angle of 90 degrees. So the vectors are perpendicular. Let's use our formula for the dot product, the scalar product, the modulus of the first one, the modulus of the second one, times the cosine of the angle between the two. Let's use that formula in this specific case when the vectors are perpendicular. Well, we want the length of the first one. That's still the modulus of A. The length of the second one will be the modulus of B. And this time we want the cosine of theta, but theta is 90 degrees. We want the cosine of 90 degrees. Now, you either should know, or you can easily check on your calculator, that the cosine of 90 degrees is 0. So these two vectors, these two moduli, whatever they are multiplied by 0. So the answer that we'll get will be 0. This is a very important result, that if you have two vectors which are perpendicular, their scalar product is 0. So for two perpendicular vectors, A and B, it's an important result which you should learn, that their dot product, their scalar product, is 0. Now, the converse of this is also true. And by that I mean that if we choose any two vectors at all and we find their dot product and we find that the answer is 0, that will mean that provided that neither A nor B was 0, those two vectors must be perpendicular. And we'll use this as a test later on in this unit to test whether or not two given vectors are perpendicular or not. I want to move on now to look at how we calculate the scalar product of two vectors when they're given in Cartesian form. Let me remind you about Cartesian form. When we're dealing with vectors in Cartesian form, we express the vector in terms of unit vectors I, j, and k. So we might be dealing with vectors of this form: 3i minus 2j plus 7k. Vector b might be something like minus 5i plus 4j minus 3k. So when we see the vectors written down like this, with i's and j's and k's in, these vectors are now given in Cartesian form. And what we're going to learn how to do now is figure out how to calculate the dot product, the scalar product of vectors like these. Before we do that, I'd like to introduce some other important results. Let me remind you a little bit about I, j, and k. In 3 dimensions, where we have an x-axis, a y-axis, and a z-axis, we denote unit vectors along the x-axis by I, along the y-axis by j, and along the z-axis by k. And you'll notice that the vectors I, j, and k are all at 90 degrees to each other. So the angle between I and j is 90 degrees, the angle between j and k is 90 degrees, and the angle between I and k is 90 degrees. And all of these vectors, I, j, and k, are unit vectors. That means that their length is 1. Now let's just calculate the dot product of I with j. And we'll use the result we had before, the definition of the dot product, which says that we write down the length of the first vector. Now the length of I, being a unit vector, is just 1. The length of j, being a unit vector, is also 1. And we want the cosine of the angle between the two. And the angle between the two is 90 degrees. So we want the cosine of 90 degrees. And again, the cosine of 90 degrees is 0. So we find that I dot j is simply 0. We could have deduced that from the previous result that I obtained for you, which was that for any two vectors which are perpendicular, their dot product is 0. So I dot j is 0. Now the same argument tells us also that j dotted with k must be 0. Because j and k are perpendicular vectors. They're at right angles, and the angle between them is 90 degrees, and the cosine of 90 is 0. What about I and k? Well, I dotted with k must also be 0. What about dotting a vector with itself? Let's just have a look at that. Suppose we wanted I dotted with I. Well, the length of the first vector is 1. The length of the second vector is still 1. And if we're dotting a vector with itself, the angle between the two vectors must be 0. So this time we want the cosine of 0. And the cosine of 0, the cosine of 0, is 1. So we have 1 times 1 times 1, which is just 1. So if we're dotting the vector I with itself, we get 1. A similar argument will tell us that if we dot the vector j with itself, we also get 1, and if we dot the vector k with itself, we get 1. Let me summarize those important results here, and they're results that you should remember. That if you took the vector I and dotted it with itself, that would be the same as dotting j with itself, and it's the same as dotting k with itself, and in any case, we get the answer 1. If we dot I with j, we get 0. If we dot I with k, we get 0. And if we dot j with k, we also get 0. And all those results are particularly important and ones that you should become familiar with as you work through the exercises accompanying this unit. Now I want to use those results about the dot products of those unit vectors to find a way to calculate the dot product of two arbitrary vectors that are given in Cartesian form. So let's choose two arbitrary vectors. Let's suppose the first one is A1I, A2J, and A3K. So this is now an arbitrary vector A, where A1, A2, and A3 are the three Cartesian components of the vector A. And let's suppose vector B, similarly, is B1I plus B2J plus B3K. And again, B1, B2, B3 are arbitrary numbers, so this is an arbitrary vector in 3 dimensions. What I want to do is work out the dot product of A and B. So let's work it through. A dot B equals, it's the first vector, which is all this, dotted with the second vector B, which is all this. Okay. Now what we want to do now is use our distributivity rule to be able to work out, to expand these brackets and work out the individual dot products. And we can do that using the rules that we know, that in turn each one of these vectors in the first bracket multiplies each of these in the second bracket in just the normal algebraic way. So first of all we want A1I dotted with B1I, those terms. Then we want A1I dotted with B2J. And finally, A1I dotted with B3K. So that takes care of this first vector here. Then we move to the second vector. So now we want plus A2J dotted with each of these three. So it's A2J dotted with B1I. A2J dotted with B2J. And A2J dotted with B3K. And finally, this last vector in the first bracket, dotted with each of these vectors in the second bracket, will be A3K dotted with B1I plus A3K dotted with B2J and finally A3K dotted with B3K. Now this looks horrendous with all these 9 terms in here, but a lot of this is going to cancel out. Now you'll remember that any vectors which are perpendicular to each other have a dot product which is 0. Now this vector is in the I direction, and this vector is in the j direction. So A1I is perpendicular to B2j. So where we have the I term dotted with the j term, this must be 0. Similarly, any vector in the direction of I, any multiple of I, must be perpendicular to any multiple of k. So this dot product is also 0. And similarly for the A2j dot B1I, those vectors are perpendicular, their dot product is 0. A2j.b3k are perpendicular. That's 0. Similarly, that will be 0, and that will be 0. And we'll be left with 3 non-zero terms. What about this term here? A1i dot B1i. Now this is a multiple of I, and this is a multiple of I, so these two vectors are parallel. The angle between them is 0. So when we work out the dot product, we'll want the length of the first one, which is A1, the length of the second one, which is B1, and the cosine of the angle between the two. The angle between the two is 0, and the cosine of 0 is 1. So we get A1, B1 times 1. So this first term, whilst it looked quite complicated, just simplifies to A1, B1. Similarly, these two vectors here, this is a vector in the direction of j, and this is a vector in the direction of j. So the angle between the two of them is 0, the cosine of 0 is 1. So when we work out this dot product, we want the length of the first one, which is A2, the length of the second one, which is B2, multiplied by the cosine of 0. Cosine of 0 is 1, so we just get A2, B2. And finally, same argument applies here. This is a multiple of k, this is a multiple of k, so the vectors are parallel, the angle between them is 0, and the cosine of 0 is 1. So we get the length of the first being A3, length of the second being B3, and the cosine of 0 is 1. So the whole lot, all of this complicated stuff, just simplifies down at the end of the day to this very important result here. And what this result says is if you want to find the scalar product of two vectors, A and B, which are given in this Cartesian form like that, all we need to do is multiply the I components together. You see the A1, B1 is the I components multiplied together. Multiply the j components together, A2, B2. Multiply the k components together, A3, B3. And then finally add up these results. So the dot product is the sum of the products of the corresponding components. And you'll notice that the result we get here on the right-hand side doesn't have any i's or j's or k's in the answer anymore. This is purely a number. This is purely a scalar, as we'd expect when we calculate a scalar product. I'll point out also that this expression on the right, which is the sum of the products of the corresponding components, is also sometimes referred to as the inner product of A and B. So on occasions, you may hear some staff or read in some textbooks that this is called the inner product of A and B. Okay, so we have a formula now for the dot product. It's A1, B1 plus A2, B2 plus A3, B3. Again, very important result, and this will allow us to calculate the scalar product of two vectors given in Cartesian form. Let me give you an example. Suppose the first vector A is this one, 4i plus 3j plus 7k. And suppose B is the vector 2i plus 5j plus 4k. And suppose we want to calculate the scalar product A dot B. Well, this formula tells us that we multiply the corresponding I components together, A1, B1. This is A1, 4. This is B1, which is 2. So we multiply the 4 by the 2. We multiply the corresponding j components together, A2, B2. Well, this is A2, and this is B2. So we want 3 times 5. And then we multiply the corresponding k components together, A3, B3, which is 7 times 4. And we do that, and we add up all the results, and we'll get 8 plus 3 5s are 15, 7 4s are 28, and if we work those out, we shall get 28, 15, and 8 to add up to 51. So the dot product of A and B is the scalar 51. Now sometimes, instead of writing it all out like this, we can use column vector notation, and some people find it a bit easier to work with column vectors. So just let me show you how we do the same calculation if we had these vectors given not in this form, but as column vectors. Suppose we had A written as 4, 3, 7, and B written as 2, 5, 4. Then the A dotted with B would be 4, 3, 7, dotted with 2, 5, 4. Now to multiply corresponding components together, it's quite easy to see what they are now, because we want 4 times 2, which is 8, 3 times 5, which is 15, and 7 times 4, which is 28. And if we add those up, we'll get 51, like we did over here. So some people might find it a bit easier just to write them as column vectors, and then just read off the corresponding components, multiply them together, and add them up to get the result. Now, it's so important that you know how to calculate a scalar product that I'm going to give you one more example, just to make sure that you understand the process. And we'll go straight into column vector notation. Suppose the vector A is the vector minus 6, 3, minus 11. That's minus 6i plus 3j minus 11k. And let's suppose the vector B is the vector 12, 0, 4. That's 12i, 0j plus 4k. So the dot product A dot B will be minus 6, 3, minus 11, dotted with 12, 0, 4. And in the column vector notation, it's so easy to work this out. We want minus 6 times 12, which is minus 72. 3 times 0 is 0. And minus 11 times 4 is minus 44. And if we add these up, we get minus 116. So the dot product of A and B is just the sum of the products of the corresponding components. I want to move on now to look at some applications of the scalar product. And the first application is one that I mentioned very early on, and it's to do with testing whether or not two given vectors are perpendicular or not. Now you'll remember from the definition of the scalar product of two vectors, A dot B, that it's the modulus of the first one times the modulus of the second one times the cosine of the angle in between the two vectors. Now if we find that when we work this out that the result is 0, then either the modulus of A must be 0, or the modulus of B must be 0, or alternatively cosine theta must be 0. Now if we know that the two given vectors do not have a 0 length, in other words the modulus of A can't be 0 and the modulus of B can't be 0, then the only conclusion we can draw is that cosine theta must be 0, and from that we deduce that theta must be 90 degrees. In other words, if we take the dot product of two vectors and we find we get the answer 0, then provided the two vectors were non-zero vectors, we can deduce that A and B must be perpendicular vectors. So, if A and B are non-zero vectors, such that A dot B, when we work it out, turns out to be 0, then A and B are perpendicular. They're at right angles. Another word we sometimes use is orthogonal. You may hear that, particularly in more advanced work. Two vectors at right angles, two vectors which are perpendicular, are sometimes said to be orthogonal. So we have a test here. We take the two vectors, we find their dot product, and if the answer that we get is 0, then we deduce that the two vectors must be perpendicular. So that's a very easy test we can apply to see if two vectors are perpendicular. Let me give you an example. Suppose we have the vector A, which is the vector 3, 2, minus 1, and the vector B, which is 1, minus 2, minus 1. Now, I think you would agree that just by looking at these vectors, 3i plus 2j minus k, and 1i minus 2j minus k, you'd have no idea, just from looking at them written down like that, whether or not these vectors were at right angles to each other. We can apply this dot product test and work out A dot B to see what happens. So let's work out A dot B. We want the dot product of 3, 2, minus 1 with 1, minus 2, minus 1. And we'll get 3 ones are 3. 2 times minus 2 is minus 4. And minus 1 times minus 1 is plus 1. So we've got 3 and 1, which is 4 minus 4, which is 0. So you'll see that when we work out the dot product of these two non-zero vectors, the answer that we get is 0. So we can deduce from this result that this vector A must be at right angles to this vector B. And that's something that's not obvious just from looking at it. So we've got a very useful test there to test whether two vectors are perpendicular or not. Now, another important application of the scalar product is to finding the angle between two given vectors. Let me remind you of the definition of the scalar product again, because we'll need that. The scalar product of A and B is found by taking the length of the first vector times the length of the second vector times the cosine of the angle in between the two vectors. So if we get two vectors in Cartesian form, and we calculate their dot product, and if we know how to calculate the modulus of each of those two vectors, then the only thing in this expression that we don't know is cosine theta. So we'll be able to use this definition to calculate cosine theta, the cosine of the angle between the two vectors, from which we can deduce the angle itself. Okay, let's rearrange this. If we divide both sides by the modulus of A and the modulus of B, we'll be able to get cosine theta is A dot B divided by the modulus of A, modulus of B. And that's the formula that we're going to use in a minute to find cosine theta and hence theta. Now, we've done a lot of work already in this unit on calculating the dot product. Let me just remind you a little bit about how you find the modulus of a vector when it's given in Cartesian form. If we have a vector A, which is A1i plus A2j plus A3k, then the modulus of this vector is found by squaring the individual components, adding them, and finally taking the square root of the result. So this is the formula that we're going to use for finding the modulus of a vector in Cartesian form. And this has been covered in an earlier year unit if you need to look back at that. Let's look at a specific example where we want to find the angle between two vectors. So the problem is, find the angle between. And the two vectors I'm going to choose are A, which is 4i plus 3j plus 7k, and B, which is 2i plus 5j plus 4k. So two vectors given in Cartesian form, and the problem is to find the angle between them. And we have this result that we've just deduced, that the cosine of the required angle is the dot product a dot b divided by the length of a times the length of b. So that's the formula that we're going to use. Okay, a dot b. Now, in fact, a dot b has already been evaluated in an earlier example, but I'll just remind you of that. A dot b, if we use the column vector notation, will be 4, 3, 7, dotted with 2, 5, 4, which is 4 2s are 8, 3 5s 15, and 7 4s are 28. And if you work that out, you'll find you get 51. So all we need to do is calculate now the modulus of A and the modulus of B, and then we've got everything we need to know to put in the right-hand side of this formula. Okay, the modulus of A. Now, the modulus of A is found by taking the square root of the squares of these components added up. So we want 4 squared, 3 squared, 7 squared, which is going to be the square root of 16, 3 3s are 9, 7 7s are 49, and if you work that out, you'll find that that's the square root of 74. Similarly, the modulus of B will be the square root of 2 squared plus 5 squared plus 4 squared, which is the square root of 4 plus 25 plus 16, and 25 plus 4 plus 16 is 45. So we've got all the ingredients we need now to pop into this formula. Cosine theta will be A dotted with B, which we found was 51, divided by the modulus of A, which is the square root of 74, the modulus of B, which is the square root of 45. Now we'll need a calculator to work this out. We want 51 divided by the square root of 74 divided by the square root of 45, which is 0.8838 to 4 decimal places. That's the cosine of the angle between the two vectors A and B. If we find the inverse cosine of 0.8838, which is 27.90 degrees. So there we've seen how we can use the scalar product to find the angle between two vectors when they're given in Cartesian form. Now there's one more application I'd like to tell you about, and it's concerned with finding the component of one vector in the direction of a second vector. Let me give you an example. Suppose we have a vector A, and we have a second vector B, and I've drawn these vectors so that their tails coincide, and as usual, the angle between the two vectors is theta. Let's call this point O, and what I'm going to do is I'm going to drop a perpendicular from this point, which I'll call B, down to meet the vector A. Let's call this point here A. Then we can regard the vector OB as the sum of the vector from O to capital A and then the vector from A to B. In other words, the vector OB is the sum of OA plus AB. Now this vector here, which we've called OA, that vector is said to be the component of B in the direction of A. You'll see we can regard B as being made up of two components, one in the direction of A and one which is at right angles to that. So this component, OA, is the component of B in the direction of A. And what we're going to do is we're going to see how we can use the scalar product to find this component. Let's call this length here, the length from O to A, let's call that little l. And then let's focus our attention on this right-angled triangle OBA. So there's a right angle in there. Now, using our knowledge of trigonometry, we can write down that the cosine of this angle is adjacent over hypotenuse. So the cosine of theta is this length, L, the adjacent side, over the hypotenuse. Now the hypotenuse is the length of this side, and the length of this side is the modulus of vector B. Now, in other words, if we rearrange this, L, the component of B in the direction of A, we can write as the modulus of B times the cosine of theta. Now, we've already got an expression for the cosine of this angle in the previous work that we've done. We already know that the cosine of theta can be written as the dot product of A and B divided by the modulus of A times the modulus of B. That's the result we've just had. So if we look at this expression now, you'll see with a modulus of B in the numerator and a modulus of B in the denominator, they cancel. So we can write this as A dot B over the modulus of A. Let me write that down again on the next page. So this, remember, L is the component of B in the direction of A. We can write it like this. I'm going to rearrange this a little bit to write it as A divided by the modulus of A, dotted with vector B. And because of a result we got very early on the commutativity of the dot product, we can write this as B dot A divided by the modulus of A. Now, when you take any vector and you divide it by its modulus, what you get is a unit vector in the direction of that vector. And we write a unit vector as the vector with a little hat on, like that. So this is a unit vector in the direction of A. So this is an important result we've got. We've got L, which is the component of B in the direction of A, can be found by taking the dot product of B with a unit vector in the direction of A. So suppose we wish to find the component of vector B, which is 3i plus j plus 4k, in the direction of the vector A, which is I minus j plus k. What we want to do is evaluate B dotted with A divided by the modulus of A. Now we can do that as follows. We can work out the dot product B dot A and then divide by the modulus of A. So B dot A is going to be 3 times 1, which is 3, plus 1 times minus 1, which is minus 1, plus 4 times 1, which is 4, all divided by the modulus of A, which is the square root of 1 squared plus minus 1 squared plus 1 squared, which is the square root of 3. And if we work that out, we'll get 3 minus 1 is 2 plus 4 is 6, 6 over root 3. This means that the component of B in the direction of A is 6 over root 3. We might want to write that in an alternative form just to tidy it up so we don't have the square root in the denominator, and we can do that by multiplying top and bottom by the square root of 3, which will produce root 3 times root 3 in the denominator, which is 3, and 3 into 6 goes twice, so that will just simplify to 2 square root of 3. So in this unit, we've introduced the scalar product, learned how to calculate it, and looked at some of its properties and applications.